This is Cambridge IGCSE Chemistry, Paper 6, Alternative to Practical, Variant 2, from February-March 2019. Question number 1. A chemist heated solid zinc chloride until it became molten. The apparatus shown was then used to pass electricity through the molten zinc chloride using inert electrodes. A silver-colored solid was formed at the negative electrode, which is the cathode. A. Name the process of breaking down a substance using electricity. So this process is coined as electrolysis. All right, it's coined the term electrolysis. B. A Bunsen burner was used to heat the zinc chloride. Describe how a Bunsen burner is adjusted to give a very hot flame. So in order to operate a Bunsen burner in the correct manner is to open the air hole of the Bunsen burner when you're operating the Bunsen burner. All right, because you have to open the air hole so that oxygen can get into the Bunsen burner and essentially supports the combustion process. Now, C. Suggest and explain the expected observation at the positive electrode, which is the anode. Now, at the positive electrode, it's the anode, and we expect to see anions getting discharged at the anode. Okay, so the zinc was already mentioned that zinc is going to get discharged to the cathode, so it will be the chloride that gets discharged at the anode. When chloride ions get discharged, essentially the charge is removed and that forms chlorine gas. All right, so the main point here is that chlorine gas is formed. And what is the observation? What can you see from the experiment is you will see that green gas is formed. All right, so green gas is formed, and then explain. So chlorine gas is formed. All right, so the identity of the green gas is actually chlorine gas. Now, moving on to D, suggest why iron electrodes cannot be used in this experiment. As mentioned in the question itself, it says that this experiment is carried out using inert electrodes. Inert electrodes are usually used because we do not want electrodes to affect the outcome. All right, you're doing electrolysis of zinc chloride. So these electrodes only serves as conductors in the experiment. All right, but if you choose to use not inert electrodes like iron, okay, so iron is actually not inert, it will actually affect the reaction by maybe reacting with one of the materials, one of the substances in the setup. So in this case, right, we say that chlorine gas is formed at the anode. So actually iron can react with the chlorine gas. So essentially you may also say that iron reacts with the chlorine gas form. Can react with the chlorine gas form. All right, so that's the answer for D. Okay, moving on to E1. What difference would the chemist observe at the negative electrode if aqueous zinc chloride were used rather than molten zinc chloride? Explain your answer. Now, we know that the purpose of doing molten zinc chloride is to get the pure substances, zinc, and also chlorine gas. If you choose to use aqueous zinc chloride, you are introducing water into the setup, and that will actually affect the reaction. So at the negative electrode, which is the cathode, for electrolysis of aqueous solutions, we will expect either a metal being formed at the cathode, or hydrogen gas. All right. And it will depend on the reactivity series. Please have a look at the reactivity series to know more. So in this case, you will see that efflorescence occur, okay, which means that hydrogen gas is formed instead of having the zinc formed at the cathode. Why? Because hydrogen is located in below zinc in the reactivity series. So hydrogen, if it's present, it's going to get discharged instead. All right. So two, when electricity is used to break down concentrated aqueous zinc chloride, chlorine is produced at the positive electrode. Describe a test for chlorine. Now, chlorine is commonly found in certain household materials like bleach. Okay, and then chlorine is characterized by its feature of being able to bleach substances. We call this bleaching effect. So how can you prove that the substance formed at the positive electrode is chlorine? By simply taking a litmus paper, okay, and then the litmus paper will actually turn white, or you may say that it gets bleached. All right, so that's the answer for 2. Moving on to F, the bottle of zinc chloride is labeled corrosive. State one safety precaution that should have been taken when using zinc chloride. So essentially, we need to be more careful in terms of wearing safety goggles, or you can choose to wear, okay, it's not exactly an option, you have to wear safety gloves. All right, just be careful when handling corrosive chemicals. Moving on to number 2. All right, a student investigated the reaction between two different solutions, A and B, of aqueous potassium manganate 7 and solution C. So A and B are potassium manganate 7 solutions. Okay, and solution C, we did not have any data regarding what solution C. 3 experiments were done. Experiment 1, a burette was filled with solution A. So a burette was filled with solution A. The initial burette reading was recorded. A measuring cylinder was used to pour 25 cm³ of solution C into a conical flask. So you have a conical flask, and that contains C. Solution A was added to the conical flask until the mixture just turned pink. So you are adding A and C together. The final burette reading was recorded. About 2 cm³ of the contents of the conical flask was poured into a test tube to use in experiment 3. So essentially, you take some of the reacted mixture and put it for experiment 3. We are not sure what's experiment 3, but we'll see that later. The rest of the contents of the conical flask was poured away. The conical flask was rinsed with distilled water. A. Use the burette diagrams to record the burette readings in a table and complete the table. So we have the initial burette reading and also the final burette reading. So let's just read it directly. This one will be 1.1 for the initial burette reading. And then for the final burette reading, we see that this is actually 16.1, which means that the volume of the solution used is actually 15.0. By taking 16.1, take away 1.1, and that leaves you with 15.0. Moving on to experiment 2. The contents of the burette used in experiment 1 were poured away and the burette was rinsed with distilled water. The burette was then rinsed with solution B. Experiment 1 was repeated using solution B instead of solution A. So essentially is the exact same setup, but instead you're doing it for solution B instead. Now, B, use the burette diagrams to record the burette readings in the table and complete the table. So you have the initial burette reading and also the final burette reading again. So the initial burette reading, as observed, it's 1.9. The final burette reading is 31.9. So makes the volume used equals to 30.0. So C1. Which solution of potassium manganate 7, solution A or solution B, is the more concentrated? Explain your answer. So this is a titration reaction, essentially. And what we see here is that the volume of B is 30.0 cm cube, and volume of A is 15.0 cubic centimeters. In other words, volume of, sorry, let me rephrase that. Essentially, B is the dilute solution, whereas A is the concentrated solution. Right, because you need less A to titrate C compared to using B to titrate C. Okay, so that will be the answer for C1 will be solution A. Why? Because you are technically using less volume of solution A is used compared to solution B to complete the reaction. Now, 2. How many times more concentrated is this solution of potassium manganate 7? So it will be, because the volume used is doubled, essentially the concentration is half. All right, it's basically B is having half of the concentration of A. In other words, A is 2 times. All right, solution A is 2 times as concentrated as solution B. All right, moving on to D1. Predict the volume of solution B that would be used if experiment 2 were repeated using 50 cm cube of solution C. So just now what we discussed regarding the experiment is, for C, so far you're using 25 cm cube. The issue that may appear in this reaction is that in order to titrate 25 cm cube of C, you need 30 cm cube of B. So if you're using the double the amount of C, which is 50, it means that solution B will be doubled. Right, because you see 25 cm cube of C, okay, needs 30 cm cube of B. So essentially 50 of that of C will need 60 cm cube of B. So it will be 60 cm cube. Please do not leave your answers as appropriate, like approximate answers, because it's a proportion question. So you have to give me exactly 60 cm cube. All right. The answer will be, this is because the volume of solution C is doubled. Right, so the ratio is 25 to 30, meaning 50 to 60 for B to C. Now, 2, suggest a practical problem that using 50 cm cube of solution C could cause. How could this problem be solved? You see, this is D2, which means that it is related to D1. You see, because you're using 60 cm cube of solution B, and the setup is using a burette. A burette maximum capacity is usually 50 cm cube only. So 60 is slightly too much. All right, you will need to you need to fill in the burette twice, essentially. Okay, so the problem here is that volume of B is 60 cm cube, which is more than a burette's capacity. All right, so you should be using, so you can, how do you solve this problem? Just review the burette again. So you may use more than one burette, or you can simply just refill the burette, okay, in between the experiment. Right, now look at E. Give one advantage and one disadvantage of using a measuring cylinder rather than a pipette for a solution C. This is more of a theoretical knowledge. Measuring cylinders are easy to use. That's why we like them. Easy to use / easy to handle. But the problem is that it is not as accurate as a pipette. All right, that's the answer for E. Moving on to experiment 3. The results from experiment 3 are shown in the table. So you have 2 tests and also observations according to the test. The first test is having aqueous sodium hydroxide was added to about 2 cm cube of solution C, and you form a green precipitate. On the other hand, you have also another test using sodium hydroxide was added to the reaction mixture saved from experiment 1. So you are forming a red-brown precipitate. Now, whenever you see the word sodium hydroxide, okay, you should think of it as one, either as an alkali. Second is they are actually cation test reagent. Okay, using an alkali and test basically the presence of cations. And whenever you see green precipitate, you should think of ions like iron 2 or chromium 3. And then red brown precipitate, you should think of the one being popular is iron 3 ions. So pretty much you can see the trend here, iron 2 and iron 3. Right, after the reaction, it may get oxidized. And in fact, this solution, potassium manganate 7 solution, is actually an oxidizing agent. right? So what conclusions can be drawn about solution C from experiment 3? So solution C contains iron 2 ion. All right, that's why it forms a green precipitate after you add sodium hydroxide. And then you can also say that the iron 2 ions, because it's a 2-mark question, can get oxidized by solution A to form iron 3 ions, which is why you got a red brown precipitate. So remember, iron 2 is green, iron 3 is brown in most of the cases. Right, moving on to number 3, two substances, solution D and solid E, were analyzed. Solution D was dilute sulfuric acid. Tests were done on the substances. Tests on solution D complete the expected observations. Solution D was divided into 4 equal portions in 4 test tubes. A. The pH of the first portion of solution D was tested. Since it's already mentioned that solution D was dilute sulfuric acid, and we know that sulfuric acids are actually strong acids, which means that the pH will generally fall between 1 to 3. Okay, so you can give me as 1 or 2 or 3. Moving on to B, a strip of magnesium ribbon was added to the second portion of solution D. So you are taking magnesium strip, putting into sulfuric acid. So we know that metals plus acid gives you hydrogen gas. So the observation will be, well, efflorescence and this is a 3 marks question, which means that we have to further show what are the observations of the gas form. So it will be, how can we prove that it's actually hydrogen gas? You can bring a lighted wooden splint near the mouth of the test tube and a sizzling pop sound is heard. All right. So looking at C, dilute nitric acid and aqueous silver nitrate were added to the third portion of solution D. Observations. So what's the main point here? Usually nitric acid doesn't do much other than providing an acidic medium. Okay, it usually is not exactly reactive. And then for aqueous silver nitrate, the main point is the silver ion. Okay, nitrate also does nothing. Okay, it's just there for exactly, well, it's just being there. The silver is the important point. Silver ions are special because they react exclusively with halide ions. Okay, like for example, fluorides, iodides. Okay, so it forms silver halides in the process, which is a white precipitate. But you see, this experiment, solution D is not a halide solution, which means that this reaction won't happen at all. So there will be no observations, slash you can just say no precipitate is formed in this reaction. Okay, so regarding D, dilute nitric acid is and barium aqueous barium nitrate were added to the fourth portion of solution D. As usual, nitric acid does nothing. It's just an acidic medium. Nitrate also does nothing, but barium does something. Whenever you see the word barium, you should think of it as the test for sulfate ions because it reacts with sulfate ions to form barium sulfate, which is a white precipitate. Okay, so in fact, sulfuric acid does have sulfate ions in it. So which means that this reaction will occur. It will occur, and hence you will form a white precipitate. Okay, by the way, let me change this word. It's not exactly sizzling. The better word is using squeaky for the hydrogen gas. Okay, moving on to test on solid E. Some of the tests and observations are shown. So test on solid E and the observation. The appearance of solid E was studied, so it's a white solid. All right, so white solid means that usually it is contains non-transition elements because we know that transition elements they are special in terms of they have like a variety of colors, but if it's white, if it's boring, means that it is it most likely contains no transition elements. Test 1. Solid E was heated gently and then more strongly. Distilled water was added to the residue and the pH of the mixture was tested. So you're doing heating and you are adding distilled water and testing the pH. So pH 10 means that it's basic. Okay, so usually basic substances, bases, we should think of possible answers are metal oxides. Metal oxides, usually, in most of the cases. Okay, but let's not make any conclusions first. Moving on to test 2. Dilute hydrochloric acid was added to solid E. The gas produced was tested. Distilled water was added to the solution and the mixture was shaken. And an excess of aqueous sodium hydroxide was added to the mixture. All right, so let's look at the first part first. Adding an acid, it produces effervescence, and lime water turns milky. When you see this phrase, you should think of carbon dioxide gas. So when you add acid with a special substance, it gives you carbon dioxide gas. So what is this special substance? Usually it will be a carbonate salt, or should I say metal carbonates. All right, so moving on to the next part, which is adding sodium hydroxide. So as mentioned, sodium hydroxide is a cation test, and it shows white precipitate form which was insoluble in excess. So you can have a look at the cation test table. Okay, so this is for calcium or magnesium ions. Okay, so let's look at E. Identify the gas produced in test 2. So this gas is actually carbon dioxide, as we have analyzed. And for F, what conclusions can you draw about solid E? So solid E is most likely calcium carbonate or magnesium carbonate. Right, because let's just check everything all together. First of all, it is white color for non-transition elements, which means magnesium and calcium. Okay, or calcium. okay, which is correct. And then when you take carbonate salts, and heat it, it will form carbon dioxide and water. Sorry, not water, metal oxides, which is why it's basic. So you have a carbonate salt heated, and that gets you carbon dioxide and metal oxides. So we are on the right track actually. Right.